So we have a theoretical background at this point and some examples about inference. Now we'll talk about some of the practical implications of inference. The objectives: to describe the conditions necessary for inference, describe cautions about confidence intervals, describe cautions about significance tests, calculate the sample size for a desired margin of error in a confidence interval. We'll define and talk about type 1 and type 2 errors, and talk about the power of a significance test. So far we have met two procedures for statistical inference. When the simple conditions are true, that is, when the data are from a simple random sample, the population has a normal distribution, and we know the standard deviation of the population, then we can construct a confidence interval for the population mean using the confidence interval formula. We can test a hypothesis that a mean equals a certain value, hypothesized value, using the one sample z statistics. These are called z procedures because they both involve a one sample z statistic and use the standard normal distribution. Now, any confidence interval or significance test can be trusted only under specific conditions. So of concern, primary, one of the first questions, where did the data come from? So when we use statistical inference, you're acting as if your data are a random sample or come from a randomized comparative experiment. If your data don't come from a random sample, your conclusions may be challenged. Practical problems such as non-response or dropouts from an experiment can hinder your inference. Different methods are needed for different designs. And there is no cure for fundamental flaws like voluntary response. As the saying goes, garbage in, garbage out. Second question, what is the shape of the population distribution? Many of the basic methods of inference are designed for normal populations. Any inference procedure based on sample statistics, like the sample mean, that are not resistant to outliers can be strongly influenced by a few extreme observations. And this again will have an effect on the reliability of your inference. So, concerning the shape of the population, the central limit theorem states that for large samples, the distribution of sample means is approximately normal. So the shape of the population distribution is not as important when the sample size is bigger than 30, unless there are outliers in the sample. And since we usually don't know the shape of the population distribution, we actually need to rely on the shape of the distribution of the sample. So it's important not to have outliers in the sample, since the mean is influenced by extreme values. So, some cautions about confidence intervals. A sampling distribution shows how a statistic varies in repeated random sampling. This variation causes random sampling error because the statistic misses the true parameter by some random amount. If no other source of variation or bias in the sample data influences the sample distribution. The margin of error in a confidence interval covers only random sampling errors. So practical difficulties such as undercoverage and non-response are often more serious than random sampling error. The margin of error does not take these difficulties into account. So we need to look carefully at the details of any study before you trust a confidence interval. Don't just accept it on face value. So here's an example. A Gallup poll asked a national random sample of 501 adult women to state their current weight. The mean weight of the sample was 159 pounds. We will treat these data as a random sample from a normally distributed population with standard deviation of 35. And we construct a 95% confidence interval for the mean weight of all adult women, and we find it's between about 156 and 162. Question: can we trust this interval as a 95% confidence interval for the mean weight of all U.S. adult women? So this is a simple random sample from a normally distributed population. That's good. But one difficulty here is that Gallup did not weigh the women in the sample. So the confidence interval is based upon their self-reporting of weight. People tend to underrepresent their weight. So if that's the case, this is not a trustworthy confidence interval. But if the responses are actually accurate, then there's no reason to doubt it, and we can certainly rely on this confidence interval. Some cautions about significance tests. These are widely used in most areas of statistical work. There are some points to keep in mind when we use or interpret significant tests. So, question 1, how small a p-value is convincing? The purpose of a test of significance is to describe the degree of evidence provided by the sample against the null hypothesis. So, we need to ask, how plausible is the null hypothesis? If the null hypothesis is a strongly held assumption, it may need strong evidence, a small p-value, in order to be accepted. So what are the consequences of rejecting a null hypothesis? So if rejecting the null hypothesis, for example, results in higher costs, you're going to need stronger evidence. Now we'll talk about sample size and how it affects statistical significance. Large random samples have small chance variation, so very small population effects can be highly significant if the sample is very large. Because small random samples have a lot of chance variation, even large population effects can fail to be significant if the sample is small. Also, statistical significance doesn't tell us whether an effect is large enough to be important. So statistical significance is not the same as practical significance. Beware of multiple analyses. The reasoning of statistical significance works well if you decide what effect you are seeking, design a study to search for it, and then use a test of significance to weigh the evidence you get. For example, suppose you perform 20 tests of significance. You have 20 null hypotheses. Suppose that all of those are true. Then each test has a 5% chance of being significant at the 5% level. In other words, results this extreme happen 5% of the time simply by chance. So we would actually expect that 1 out of these 20 tests would be significant simply by chance. So running one test and finding significance is good evidence of an effect. Running 20 tests and getting a significant result is not good evidence of an effect. For example, if you have a multiple choice test, just by chance you're likely to get one question correct out of, say, 20 different questions. But that doesn't mean you're going to pass the test. Now, we can calculate the sample size for a confidence interval for a particular margin of error. Remember that the margin of error for a confidence interval is given by this formula, the z-score times the standard deviation divided by the square root of the sample size. So, to determine a sample size that will yield a particular confidence interval for a population mean with a specific margin of error, we first find a reasonable value for the standard deviation of the population, either from an earlier study or a pilot study. We find the critical z-value for that particular level of confidence. And then we set the expression for the margin of error to be less than or equal to the particular margin of error, and then we solve for n. So, for example, researchers would like to estimate the mean cholesterol level of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 0.75 milligram per deciliter of the true value of the population value at a 95% confidence level. A previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. So the critical value for a 95% confidence level is 1.96. We use sigma equals 5 as our best guess for the standard deviation. Now, the desired margin of error here, 0.75. So we fill in the numbers on the left and solve for n. First, we'll use a little algebra. So first we multiply both sides by the square root of n and divide both sides by 0.75. So we're looking to isolate n. Then square both sides to get rid of the square root sign. And then if we calculate that, it comes out to be 170.74 is less than or equal to n. And we round up to 171 to ensure the margin of error is no more than 0.75 at this level of significance. So that's how many monkeys we'd need to satisfy these conditions. Now we're going to talk about type 1 and type 2 errors. We draw a conclusion from a significance test. We certainly hope that the conclusion will be correct, but sometimes it'll be wrong. There are two types of mistakes we can make. One is we reject the null hypothesis when in fact it's true. This is called a type 1 error. Or if we fail to reject the null hypothesis when in fact it's false, this is called a type 2 error. We can look at the possible outcomes here. There are 4 possible outcomes. So we have 2 possibilities for the conclusion. We either, based on the sample, we either reject the null hypothesis or fail to reject it. And there are 2 possible truths for the population. Either the null hypothesis is true or it's false, and the alternative hypothesis is true. So in 2 of those cases, for example, if we fail to reject the null hypothesis when the null hypothesis is true, that's a correct decision. Or if we reject the null hypothesis when it's false, that's also correct. In the other 2 cases, we've made an error. So, by analogy, the U.S. judicial system assumes that a person is innocent until proven guilty. So in a jury trial, there are 4 possible outcomes for a defendant. The jury can decide between 2 things, either convict or acquit. And then there's the truth about the defendant, which we really don't know. The defendant can be, in fact, either innocent or guilty. So if we convict the innocent person, that's an error. Or we can fail to convict a guilty person. That's also an error. Now, the probability of a type 1 error is actually the probability of rejecting HO when it's really true. This is exactly the significance level of the test. So, alpha is the probability that the test will reject the null hypothesis when in fact it's true. So we need to consider the consequences of a type 1 error before choosing a significance level. So again, as a reminder, type 1 error is when we reject the null when it's actually true. So suppose we have a study that's investigating whether a new curriculum is better than the current curriculum. The null hypothesis is that the new curriculum is no better than the old curriculum. A type 1 error would be to conclude that the new curriculum is better when in fact it isn't. The consequences here might be that implementing a new curriculum will cost tons of money and require retraining, getting new books, and all of that type of thing. Now, a significant test makes a type 2 error when it fails to reject a null hypothesis when it really is false. Now, there are many values of the parameter that satisfy the alternative hypothesis, so we need to concentrate on only one value. We can calculate the probability that a test does reject the null hypothesis when an alternative is true. This probability is called the power of a test against the specific alternative. The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a particular alpha level when the specific alternative value of the parameter is true. So again, type 2 error is not rejecting the null when it's actually false. So consider the study of whether a new curriculum is better than the old one. The null hypothesis was that it's no better than the old one. A type 2 error, now that should be type 2, would be to conclude that the new curriculum is not better when in fact it is. The consequences here might be that the students will not get as good an education using the old curriculum when they could be using the new one. So, how large a sample should we take when we plan to carry out a significance test? The answer depends on what alternative values of the parameter are important to detect. So, summary of influences on the question, how many observations do I need? If you insist on a smaller significance level, such as 1% rather than 5%, you need to take a larger sample. A smaller significance level requires stronger evidence to reject the null hypothesis. If you insist on high power, you will need a larger sample. Higher power gives a better chance of detecting a difference when it is really there. At any significance level and desired power, detecting a small difference requires a larger sample than detecting a large difference. So to review, we talked about some of the conditions necessary for inference, and we talked about the cautions regarding confidence level intervals and significance tests. We can calculate the sample size for a desired margin of error for a confidence interval, and we defined type 1 and type 2 errors, and talked a little bit about the power of a significance test.